Here's a table of students: ID, name, department, age. And here's a perfectly ordinary question. Give me the names of the students older than 20. To answer it, we do two small things in turn. First, keep only the rows we want, the older students. Then keep only the column we asked for, the name. Each step takes a table and hands back a smaller table. That is the whole idea of relational algebra. It is a small set of operators, and every operator is a function on tables. One or two tables go in, exactly one table comes out. Because the output is itself a table, you can feed it straight into the next operator and chain them into any query you like. It's the precise theory sitting underneath SQL. Let's meet the operators one by one and watch the table change each time. The first operator is selection, written with a Greek sigma. Sigma with a condition tucked underneath, applied to a relation R. Say it out loud as select from other rows where the condition holds. Let's run one. Sigma, age greater than 20 of students. We walk down the table and test every row against the condition. Age above 20. Asha is 22, greater than 20, so she stays. Ravi is 19. No, he goes. Maya 25. She stays. Kabir is exactly 20, and 20 is not greater than 20. So Kabir goes too. So the result is a new table with exactly two rows, Asha and Maya, and the very same four columns as before. Selection never touches the columns. It only decides which rows survive. The schema is unchanged. The second operator is projection, written with a Greek pi, with a list of attributes underneath, applied to R. Where selection was a horizontal filter on rows, projection is a vertical slice. It keeps only the columns you name and throws the rest away. Here's projection onto the department column alone. Pi, depth of students. First, we keep the depth column and drop ID, name, and age. Fade the other three columns out, and we're left with a single column of departments: CS, E, CS, EE. But we're not done. A relation is a set, and a set has no duplicate members. Look, CS appears twice, and EE appears twice. Projection must quietly collapse those repeats. After removing duplicates, the answer has just two rows, CS and EE. Four rows went in, two came out. That's the surprise in projection. Because it deletes duplicate rows, it can hand you back fewer rows than you started with. So hold the contrast firmly. Sigma filters rows with a condition. Pi picks columns from a list and dedups. Rows for selection, columns for projection. Never swap the two. Now the payoff. Our opening question, the names of students older than 20, is just these two operators composed. Pi name of sigma age greater than 20 of students. And you read a composition the way you read any nested function, from the inside out. Inner first, sigma age greater than 20, we already did. It keeps Asha and Maya with all four columns. Then the outer pi name runs on that two-row table, keeping only the name column. Asha and Maya are already distinct, so nothing collapses. The final answer is a one-column table. Asha, Maya. Exactly the names we asked for. The next three operators treat tables as plain sets of rows and combine two of them. But there's a catch. You can only combine two tables if they have the same shape. We call that being union compatible. Here are two tables, A and B. Each has a single column ID. Same one column, same domain of integers. These two are compatible. We are allowed to union, intersect, or subtract them. Now watch a mismatch. A has one column. This debts table has two ID and debt. Different numbers of columns. You simply cannot line their rows up. One next to IDCS? It's meaningless. So A union debts is undefined. The set operators are off the table until the two schemas match. Back to our compatible pair. A holds 1, 2, 3. B holds 2, 3, 4. They overlap on 2 and 3. Keep them both in view. We'll run all three set operators on them. Union. The cup symbol is every row in either table, with duplicates removed. Pour A and B together. 1, 2, 3, 4. 2 and 3 appear in both, but each shows up only once. 4 rows. Intersection. The cap symbol keeps only the rows in both tables. The only IDs sitting in A and in B are 2 and 3. So the result is just 2 and 3, 2 rows. Difference. A minus B keeps the rows in A that are not in B. A has 1, 2, 3, strip out 2 and 3 because they're also in B, and 1 is left alone. Just a single row, and here's the one that trips people. Difference is not symmetric. Flip it, B minus A, and you get the rows in B, but not in A, which is 4. 1 minus the other gives 1. The other way gives 4. A minus B is not B minus A. The last operator here is the Cartesian product, the cross. Our cross S pairs every single row of R with every single row of S. Unlike the set operators, the two tables need not match at all. Their columns simply sit side by side in the result. Take two tiny tables. Colors, red and blue, 2 rows. Sizes, small, medium, large, 3 rows. Now form colors cross sizes. Each color meets each size. Red with small, red with medium, red with large. Then blue with small, blue with medium, blue with large. The result has both columns, color and size, and every combination shows up exactly once. Count them. 6 rows. 2 colors times 3 sizes is 6. The size of a product is always the 2 row counts multiplied, not added. And you can feel it explode. 100 rows crossed with 100 rows is 10,000. On its own, a product mostly makes a mess. Its real job is to be the raw material for something better. Pair every row. Then use selection to keep only the pairs that belong together. And that combination, product then select, is exactly what a join is. We build joins next. Your turn. Same students table. Evaluate pi depth of sigma age at least 21 of students. Pause right now and work out the exact result table. Watch the ages carefully. And don't forget what projection does at the end. I'll wait. Inside out. First sigma. Age at least 21. Asha is 22. Yes. Ravi 19. No. Maya 25. Yes. Kabir 20. 20 is below 21. So no. That keeps Asha and Maya. So after selection, we have two rows. Asha in CS and Maya in CS. Now project onto depth. Both rows have department CS. So we get CS and CS. But projection removes duplicates, and the two collapse into one. The final answer is a single row, CS. If you kept both, that's the classic slip. Projection always dedups. Trap 1. And the most common. Swapping sigma and pi. Sigma takes a condition and filters rows. Pi takes a list of columns and slices them out. Rows for sigma, columns for pi. Trap 2. Forgetting that projection dedups. Drop enough columns and rows that used to differ become identical, and the extras vanish. Projection can shrink the row count. Trap 3. Union, intersection, or difference across mismatched tables. They demand the same arity and matching domains. Different shapes, and the operation is simply undefined. Trap 4. Assuming difference is symmetric. A minus b keeps what's only in A. B minus A keeps what's only in B. They are different tables. Order matters. And trap 5. The product. Its size is the two counts multiplied, never added, and it grows fast, so it's rarely used bare. And always evaluate a composition from the inside out. Let's lock it all in. Selection, sigma, keeps the rows that satisfy a condition. A horizontal filter that leaves the columns untouched. Projection pi keeps only the columns you name and then removes duplicate rows. So its result is a genuine set and can be smaller than you'd expect. Union, intersection, and difference treat tables as sets, but only when they're union compatible, the same columns and domains. And remember, difference is not symmetric, and the Cartesian product pairs every row with every row, multiplying the counts. On its own, it explodes. Paired with selection, it becomes the join. Master these operators, and you can read any relational query and every line of SQL that rests on them.